First, let me give a quick introduction on some of the models we're going to use for Project 2. Project 2, as I mentioned in the post, and it is the type of machine learning models you would build in reality, meaning your model need to continue to learn. For example, at the very beginning, our training data contains 13 months of data. Then you're going to use that data to fit a model, and then predict weeks in the first fold. I call it test 1. And then once you observe the weekly sales from fold 1, you can evaluate, and also you can add that the orange data from fold 1 into your training. Now you get a larger training set. You're going to retrain a model and then predict weeks in fold 2. And then once you observe the weekly sales from fold 2, you're going to evaluate the accuracy, and now going to add that green bar into our training data and continue this process until we finish predicting for the 10 folds. So you can look at Josh's code to understand the structure of the code, how you can continue to train your model, do prediction, and add the training data into your training and go through the whole process. Let me quickly review some of the models we're going to use. And my old.train would be all the data, and let's assume we're going to work form prediction for fold 8, so t is equal to 8. Then I'm going to find out the starting and ending dates for fold 8. And then we're going to focus on department 5, so DEPT is equal to 5. And here, this is how I extract data related to department 5. I will take all the training data, first go through the filter where we only extract data they are before the starting date of fold 8, and only retrieve data the department is equal to 5. And then we only focus on variables like store, date, and weekly sales. And the last command is spread will arrange those data, the weekly sales, as columns by stores. So the data is arranged on the right. It is a matrix with 117 rows and 46 columns. The 117 rows because before fold 8, we totally observe the duration of the date will be 812 days. So if you divide it by 7, you will get 116. So plus the starting week, we're going to have totally 117 weeks of data. So this is why our the date will be 117. So the data matrix has 46 columns. The first column will be just the date, and the second column will be the store weekly sales for store 1 over the 117 weeks, and third column will be the weekly sales for store 2 all the way. The last column, which is column 46, will be the weekly sale for store 45. Let's focus on store 2, so that's the third column of this data matrix. So let's retrieve the third column, and we tell R this is a time series and the frequency is 52. And then let's just predict the next 7 weeks. Here I didn't really count how many weeks in fold 8. I just predict the next 7 weeks. And the first method is the so-called naive method. What is naive method? We have data which is a blue bar from week 1 to week 117. So the most recent observation is observation at week 117. Then we're going to just take that weekly sale and use that number to predict all the weekly sales in the next 7 weeks. So we're going to get 7 identical predictions. So this is called a naive method. And this may work well for a stock price, but it doesn't work well for this data because we can clearly see the seasonal pattern over the 52 weeks. So the next method is called a seasonal naive. It works as follows. we're going to predict the next 7 weeks because the most recent week is 117. So for the next 7 weeks would be week 118 all the way to week 125, and those numbers are colored in red. So we're going to, for example, for week 118, we're just going to go back a year. So we're going to count back 52 weeks, and that's week 66. So we're going to use the weekly sale from week 66 to predict the weekly sale for 118. So my last year index, you're going to find out that that's basically the index for from last year, the row numbers for the weeks, and if we look a year back. So basically we're going to use sales from week 66 to 72 to predict week 118 to 124, and that's called seasonal naive. And the third method is called TSLM, and based on the name, it's just basically a linear regression model. So we're going to fit a linear regression model with 2 predictors. One is season, and it will be a categorical variable with 52 levels. Another is trend, and it will be numerical. So it's almost like a week plus year. You might be wondering, all we pass to our R command TSLM, is this store-ts? It is a column, a data vector of length 117. So where we can find out the other 2 predictors like season and trend. Well, we've also told R, and the store TS is a time series with a frequency 52. So here's how we're going to generate the season and trend. Let's look at the blue bar. That's the data and 117 rows. So for every observation, we look at its row number and take that number divided by 52. So the remainder going to be season and the integer part going to be trend. For example, for row 1, number 1 divided by 52, the remainder is 1, the integer is 0. For row 2, so 2 divided by 52, the integer is 0 and the remainder is 2. Now for row 66, 66 divided by 52, the integer is 1 and the remainder is 14. All the way to the last observation, row 117 divided by 52, the integer is 2 and the remainder is 13. So the season is going to take 52 different values, 1, 2, all the way to 51, and then 0. So there are 52 different values. It is almost same as our variable week. Remember, for our first observation, the corresponding week is actually 5. Here we just sort of relabel it as 1. That wouldn't make any difference because season just going to be treated as a categorical variable unordered with 52 levels. And the trend basically is our year. So we can just fit a linear regression model using the blue bar and with predictor season and trend. And then we can form our prediction for the next 7 weeks, because for the next 7 weeks, we just add those weeks at the bottom of this blue bar. And so they're going to start from row 118 to row 124. Again, we can compute the corresponding season and the trend, and we plug into our linear model, and we can get our prediction. And here I show you 2 ways to compute the prediction. And for the first set of code, we just use a TSLM command. And the remaining block here, I just create the fit a linear model, and by first constructing season and trend, and then do the prediction. You're going to find out the prediction from the 2 sets of code should be identical. And here we treat our season as a categorical variable with 52 levels, meaning we're going to fit, in addition to the intercept, we're going to add another 51 coefficients. A better way to fit trend is season is just to fit season by using a non-parametric curve estimation procedure like Lois. So the TSL, which is another model, where we're going to model this seasonal pattern and also the trend, both using Loess non-parametric curve estimation. But for that model, you have to have at least 2 years of data. So you can start using that model once after fold 6. You're going to find out that model indeed works much better than the other. You can dramatically reduce the estimation error. And so those are the models you can try for project 2. Before talking about linear logistic regression model, I want to clear some jargons. Previously, we talked about discriminant analysis like LDA, QDA, or naive Bayes. It should be naive Bayes. And they are called generative model because we actually learn the joint distribution on both X and Y, so we can actually generate, and those models can help us to generate data, the pair X and Y. And starting from this week, we're going to learn directly learn the conditional distribution of Y given X, which is often called a discriminative model, like logistic, SVM, and tree model. And those models, we cannot really generate a pair of observation X and Y because when we are learning, we only learn the conditional of Y given X. We didn't put any assumption and we didn't learn anything about the marginal distribution of X. And I just want to point out the difference of jargon because discriminant analysis is not discriminative model but generative model.